If we're going to use group technology, there's a little more work we have to do related to creating part families. The goals of group technology are, of course, the overall goal of reducing manufacturing lead time. And manufacturing lead time, if you recall, is the total time for the part to go from the beginning of our set of processes in the material flow process chart to finished goods. We'd also like to reduce the work in process. In other words, reduce the amount of time that we spend waiting to go through a process, and that will involve reducing variability. It will also help us improve scheduling because now we can take similar parts and process them in the same system. We also need to reduce the setup times so that as we switch from part to part, that there isn't a big change in our system. And if we can group, then we could use similar tooling for multiple parts and variations of parts. This will also help us increase equipment utilization. So there are a lot of positives here, but it will involve some work on our part in order to come up with a proper classification of our parts. Now, when we think about part families that correspond to our group technology, we can think of it in terms of similarities that we see in the shapes or features that we are creating. So here you see perhaps 3 different part families that we might create based upon similarities in shapes and features. But we might also want to consider the scale of the product in terms of its dimensional characteristics, so very large products versus very small. And finally, the set of processes as specified in our material flow process chart. So ideally, if I have a part family like we see here, then they all share the exact same material flow process chart. Now, in some cases, there will be variations, and the question is, to what degree will we allow the variations in our material flow process chart? If we can group those material flow process charts into a reasonable set, then we've got the basis for a group technology system in terms of configuring our individual processes. So the first step, of course, is to identify those part families. And this is based upon the principles that we saw before. We make an assessment of the degree of similarities between product specifications. That can be done just by looking at the design spec and or physical parts, or we could come up with a mechanism for part classification and coding that we'll look at today. Or we could look at the material flow process chart that we've already looked at previously. And if we take that approach, then we'll call that production flow analysis, which we'll see later on. So let's start first with parts classification. Typically, and this will vary from organization to organization, a company will come up with a set of codes, as you can see here. It's an encoding scheme of some kind. And then the similarity will be based upon, in this case, the number of positions that have the same digit value. And then, of course, we could group them and break it down further, but the degree of similarity will be the degree of matching with this representation. That representation can be based upon attributes of the designs, as well as parameters such as dimensions and so forth. It could be the manufacturing attributes in terms of processes, or a combination of the design and manufacturing attributes. And then we'll create from those attributes a part family that looks quite similar. Typically, as we go from left to right, the right part of the code is going to deviate, or I should say we will allow deviations in the same part family. But there will be some segment of the code that will be shared in common for all the parts. Well, let's look at a classical example of a classification scheme, and that is the Opitz Classification. And you'll see this in many books and papers, including the one that you're reading for today. If I look at the Opitz Classification, it's based on 9 digits, and those digits can range from 0 to 9. And the first 5 digits in that 9-digit code will contain some type of information related to the design attributes. And then digits 6 through 9 will have supplemental information, including things related to manufacturing. Based upon a set of hierarchical tables, we'll classify, in other words, we will pick certain digits that correspond to each location in our 9-digit code. So I could have something like this, representing a class of parts that are going to go through the same set of processes in my manufacturing system. So I've got a 9-digit code, and if I have similar parts that share the exact same code, then it's a no-brainer. However, if I have deviations, for instance, if this is slightly different, if this digit is slightly different, we have to make a decision as to whether or not that is in the same part family. In other words, is it a major difference in terms of the processes that we'll be using? Well, let's look at the first digit. The digit 1 is based upon the size, in other words, the scale of the part, and the symmetry of the part. How symmetric is that part? The second digit has to do with the main part shape, or we can think of that as the external geometry of our part. Digit 3 will deal with internal features, and digit 4, if I have surfaces, such as flat surfaces, how do we treat those? How do we classify them? And digit 5 is kind of a catch-all where you might have gear teeth, additional holes representing features of the part. Putting all these 5 digits together, we get some type of category of parts that appear to be similar. So if we look at that digit 1 that's based upon size and symmetry, the first level classification has to do with whether it's an axial part, in other words, it has an axis of symmetry, similar to what we saw with runout and total runout, or is it asymmetric? Typically, an asymmetric part is a prismatic. So a cube would be a prismatic part. Within each category now, you can see we're breaking down the value of digit 1. We will look at the dimensional characteristics. For an axial part, it will be based upon the length upon the axis, and then the diameter, the smallest box or cylinder that we can enclose around this part, which will be the largest diameter that we encounter. And now we'll take the ratio of length to diameter, and you can see 3 categories here. So, for instance, length over diameter is greater than 3. You're talking about a relatively long part. Whereas length over diameter is less than 0.5, that's more of a flange, right? More of a thin part that's wide with respect to its length. And then this is kind of in between. For asymmetric parts, A, B, and C are length, width, and height. And now we're looking at relatively flat parts. A over B is less than 3, and then A over C is greater than 4. Or what we might consider relatively long parts, A over B is greater than 3. Cubic parts, and I'll put that in quotes, it's not exactly cubic, obviously, but you can see the ratio of A to B and A to C is in the less than 3, less than 4 range. So it's not exactly a cube, but it's similar to that. For axial parts, if you look at the second digit, then we're looking at the external shape. What does it look like from the outside? And so from the outside, what we might see is just, oh, it's a uniform cylinder, the entire length of the part. Now we might have other part features, holes and gears and so forth, but we're talking about this external shape. Or what we might see is a bit of asymmetry over the length of the part, and that is it could be stepped. It could start out with a large diameter and then decrease in diameter to the other end, or vice versa. So it could start out small and increase to the other end. Or what we might see is step to one end or uniform with a thread on it. So we might thread the outside. It wouldn't have to be the entire length, but some type of threading. Or there might be some groove in that particular feature, keyway, or an axial groove of some kind. Another possibility is some type of asymmetry where it's stepped from both ends. In other words, it is kind of diamond shaped, right? Or it could be the reverse, kind of an hourglass configuration here. Digit 5 is similar to digit 2, or value 5 for digit 2 is similar to a value of 2. They're both threaded. However, this is based upon these types of stepping. And then, of course, the groove is similar to here, except for the underlying geometry. Finally, what if we have a taper? How do we deal with that? Some type of cone shape. For digit 3 of axial parts, and of course the reason why we're covering axial parts, as you saw in the reading, a very large majority of parts fall into this category. Digit 3, we have internal shapes. So we might have a blind hole at one end or the other. We could have a hole that is stepped, right? So it changes in diameter. Or it could be stepped or uniform, but have a thread, an internal thread now, because we're dealing with internal shapes, or an internal groove, right? A keyway and so forth. It may be stepped from both ends. Again, we might create a hole feature that gets larger as we go in from one end as well as the other. And then, of course, we can add threads to that or a groove. And then finally, that feature could be tapered from either end. These would be internal features. So here's some simple examples. Here I've got an axis of symmetry on this axial part here. And if I look at the classification, I would certainly characterize this as being stepped from this end to that end, or whatever your perspective is, you might think of it as being stepped from this end. So we have increments where we change the diameter, and hence this notion of stepping. Or in the second case, we see stepped from both ends, and here we move from the end here and step up. Of course, there can be multiple steps. These are just two possible examples. Well, here's an example of an axial part in terms of a design specification. So where we start in terms of classification? Well, hopefully you recognize that, similar to the previous example, this represents a stepped geometry. It is certainly axial with respect to this axis. So we would call this stepped from one end. So the question is, what would the Opitz code, at least those first 3 digits, correspond to? So what do I put in these first 3 digits of the Opitz code? Well, let's go back and look at those digits. So first of all, our size and symmetry. What we're looking at here is the ratio of L over D. So we've got less than 0.5, 0.5 to 3, greater than 3. Well, if we look at this ratio here, you can see, and we really don't need dimensions in this case to figure this out. We can just tell from the relative size. This length here would be our L. This would be our D. And you can see they're fairly close, so it's going to be L looking a little bit smaller than D. So roughly it's going to be in the middle range, the 0.5 to 3, right? And therefore we would put a 1 value in that first digit. The next digit had to do with the external, and we said it's already stepped from one end. And if we look at that, that's essentially going to be, well, let's go back just so you can see that. Here's our external shape. It's stepped from one end. We have no threading, no groove, and no taper, so we stay with that. So now we've got a value of 2. And then finally, the third digit that we'll have to look at has to do with the internal features. Now here we would not include the through holes here in this section. Those would be considered auxiliary holes, and that would be found in another digit. But for this third digit, we're looking at internal features, and that would be with respect to our axis here. Well, we can see that there are none, and so that kind of simplifies things. If we go back and look at that third digit, what we actually see here, and I didn't mention this, but this also corresponds to a simple blind hole or no bore at all. And if you look at going from a value of 0 to 9 in any of these digits, as you go towards the higher digits, you're dealing with high complexity, and that's kind of the thinking behind assigning a code value here, versus a low complexity. And clearly, if we look at this internal shape, which there is none, we would say there's no complexity there, and therefore we have a digit 0. So here's our Opitz code, at least the beginning of it. We still have 6 digits to go, but you get the general idea. Based upon our design specification, we can come up with perhaps a part family where the first 3 digits are 1, 2, 0, and then they would proceed through the same set of processes with perhaps some slight variations.